Hello Year 12s. In this video we're looking at automatically writing, I don't know why I've called them basic, but automatically writing integrals. And this is for learning intention 33. This is going to be broken up into two parts. So we'll call this part 1. Part 1 is kind of like a checklist. I'm going to be going through all these formulas and making sure we understand them all. So this should at the moment look like way too much information. It should look like gobbledygook, and it probably makes little sense. But once we go through them one by one, you'll go, oh, I remember what that means. And there are a few new facts down the bottom here. So this is a kind of, here are all the formulas. And in part 2, we're going to do some tricky examples. So let's look at statement number 1 here. What on earth is that talking about? We'll call this number 1. It's the linearity property of integrals. It's saying you can expand an integral, almost like you expand brackets. So let's look at an example of number 1. We'll look at it up here. Say you have something like the integral of x cubed minus a half x squared plus the natural log of x dx. So we're taking the integral of all this stuff. We don't know what this integral is. What this first property is saying is that we can kind of expand the integral out, much like we might expand brackets. So it means you can take each term and take the integral of that individual term, and it will be the same thing. So it's the same as saying x cubed dx minus the integral of a half x squared dx plus the integral of the natural log of x dx. So this first thing is just saying we can expand these out. If we have a look at a kind of another example of this, let's actually do one. So let's call it, I don't know, we'll call it 1.1. These are all relating to this first formula. Let's look at another example. If I wanted to integrate 2 minus x squared dx, well, the way I'll do that is I'll go here. Well, this is really x to the power of 0, so I'd add 1 to the power. So 2 becomes 2x. Here I add 1 to the power and divide by the new power. So that's a negative third x cubed, and that's going to be plus c. Now what this is saying is that's equivalent to expanding this out first. So the integral of 2 dx minus the integral of x squared dx, and doing each part separately. So the integral of 2 is 2x, and the integral of x squared is a third x cubed, and we've got a plus some constant on. So that's what this first statement is saying. This next statement here with the k is saying that you can take a constant out of an integral. So it's saying you can take a number out. You can't take a variable, you can take a number. So let's have a look at that. Let's call that example 2. So it's saying that if I have the integral of 3x to the power of 4, let's do that the normal way. Let's add 1 to the power and divide by the new power. So that's 3/5 x to the 5 plus c. It's saying that we're allowed to take this 3 out. you're allowed to pop the 3 out the front of the integral. And it's kind of like it's 3 times that integral. So I've taken a 3 out the front. Well, it's 3 times 3 times a fifth x to the 5, which is 3/5 x to the 5. So we can see that those are the same. And let's add our constant there. So we're allowed to take constants out. Now you are not allowed to do this. You are not allowed to take an x out. See what I've done there? I've taken an x out as well, because x times x cubed is x to the power of 4. You are not allowed to do that. You may only take out constant values. Let's have a look at number 3. This is very new. And we're going to be looking at examples of how to handle this in the next video. So I'm just going to do one. What you're doing is identifying a certain form. So this is a kind of algebraic form, and this is the general answer. Keeping in mind we can't have -1 for n. So let's do an example of that. Let's call that example 3. So let's assign some numbers here. Let's find the integral of 5x plus 5x plus 7 to the power of 3 dx. How do we find the integral of this? Well, it's saying it's ax. Well, a is 5, so it's 5x plus b, well b is 7 in this case, plus 7 to the power of n plus 1. Well, n is 3, so n plus 1 gives us 4, divided by a, which is 5, times n plus 1. So 5 times n plus 1, which is 4, plus c. Well, that equals 5x plus 7 to the power of 4 on 20 plus c. Another way to think about this is you add 1 and divide by the new power, as you usually do. So add 1 to the power, get 4, divide by the new power, but you also have to divide by the coefficient of x. That's what this is saying. So it's saying you can do your usual add 1 and divide by the new power, but divide by the coefficient of x as well. That's what this formula is saying. We can do another one of those. Let's call this 3.1. Let's do the integral of 2x plus 3 squared dx. Alright, we could expand it out and do it the long way, but now we have this shortcut. So add 1 to the power, divide by the new power, but divide by the coefficient of x as well, is what this is saying. So that equals 2x plus 3 cubed on 6 plus c. There's your answer there. Two ways to think about it. You can memorize the formula, or you can think about it as divide by the new power and divide by the coefficient of x. So I'm going to clear this now. I'm going to make some room. I might clear this away, and I might clear that just to tidy it up a bit. Let's have a look. What's next? We've got this statement. Here's a new formula. And I know I'm bombarding you with these, but the next video will do examples. So this is how we integrate 1 on x. So let's look at this, how we integrate 1 on x. So these are all linked to our derivatives. Remember, the derivative of the natural log function is 1 on x. So the integral of 1 on x must be the natural log function. So it goes both ways. So remember, if you have like, remember that you know this fact. I'll say that again. The derivative of the natural log function is 1 on x. We already know that. That means that the integral of 1 on x is the natural log function. And you always got plus some c. Now it's got these bars here. These are absolute value bars. So you can either say, there's a couple ways you can state it. You can say that x has to be greater than equal to 0, or you can put your absolute value bars in there. Depends on your domain here. Like if you know x can't be negative, then you don't need the absolute value bars. But we can put them in there to be safe. So what might an example of this look like? I'll call this 4.1. So we might have to integrate 3 on x. Well, I know, so let's assume I only know these facts. I know I can take the 3 out because the 3 is a constant. And then I know I can integrate. So that integrates to the natural log of x plus c. There we are, that's our answer. This is a more, the next one is a more general form. So it's saying that for reciprocal functions, so if it's like 1 over something, it's showing you how to integrate that. And I will go over more examples of these, but I'm just throwing all the formulas at you. So let's have a look at that. So let's look at an example of this. So if you have the integral of 1 on 3x plus 5 dx, well, that's equal to, the first thing you have to do is take the coefficient of x and go 1 over, like that, so 1/3, take the coefficient of x and put 1 over, and then it's the natural log of whatever's on the bottom, 3x plus 5, and then adding some constant. Well, how do you know that that's true? Like, why would that be true? Why would any of this be true? If you're unsure about any of this, you can go back and take the derivative and see if it takes you backwards, like we've done up here. I'll show you what I mean. So the derivative of this should be 3 on x. Let's take the derivative of this. Let's take d dx of the natural log, whoops, the natural log of x plus c. Okay, well, we know that that diffs to 1 on x, and the constant stays there, so it's 3 times 1 on x. The constant disappears. That equals 3 on x. That's what we got over here. Let's take the derivative of this. A third. I'm going to drop the absolute value bars. I'm going to assume that there's a appropriate domain restriction, just to avoid confusion. Okay, so plus c. Well, to take the derivative of that, we can just leave the third as a constant out the front. It's the diff over the original, so it's 3 over 3x plus 5. The c goes away. Those cancel. We get 1 on 3x plus 5. Sweet, that's what we have here. So you can always take the derivative to go backwards. So let's clear that. You can take the derivative to check if you have the right answer. Number 6. Here we are. We've got our favourite, our e. We have our exponential function. Well, if you remember, the derivative of the exponential function is the exponential function. So the integral of the exponential function must be the exponential function. And it's true, it is. Goes both ways. It's very nice. They've given us a bit of extra information here with a constant. So if you say need to integrate e to the power of 3x dx, well, integrating that, what you do is instead of bringing the power down, you divide by the power. So instead of timesing by the power out the front, you divide by the power. So it's 1/3 e to the power of 3x plus c is the integral there. So that's number 6. And 7 is our sine function. So if you remember, cos diffs to negative sine, so sine must integrate to negative cos. So if you've got like the integral of sine of x dx, that's negative cos of x, because cos diffs to negative sine, so sine must integrate to negative cos. I hope that makes some sense. Let's look at an example of that. So using this formula, so you might have sine of 3x dx equals, well, a is 3 in this case, so we have negative 1/3 cos 3x plus our constant there. There you are. Sine integrates to negative cos. And we've got negative 1/3 cos 3x plus c. And it's a similar sort of thing for integrating cos. Because sine diffs to cos, cos integrates to sine. So let's have a look at that example here. Let's do the same thing. Let's let a equal 3 cos of 3x dx. Well, that equals 1/3 sine 3x plus c. There we are, there's our answer. Alright, integration, for some reason, it's notoriously tricky. Like, it's just it's a challenging topic. And I doubt you would get all of that in one go. So I would recommend, just to get used to the formulas, if you're unsure, I would even watch this video again, and I'll try to pause and then have a go at doing the problem myself using the formula and then see if I've got it right. I'd recommend that. In the next video, we're going to look at examples of how to use all these formulas. And I also have to add, for learning intention 33, I've got some extra questions. I want you to do exercise 9A, and I want you to do questions 5, 7, 10, and 11. Now, just do as many as you need to understand. I'm not going to say do them all or do none of them. Just do them until you feel comfortable. There's lots of questions to practice on there. Do as many as you need to feel comfortable. And if you have been, thanks for watching.